Okay, here's a diagram that depicts the situation. The original post suggested that you use X for the angle of elevation to go over this 2-foot high fence, which is 5 feet from this building. Uh, and then use a specific value for that angle to find the length of the ladder. But we're just going to the general case. Um, there's a lot of ways to end up with this function right here, looking at this diagram. This is maybe the most straightforward. If you label the unknown parts, this distance from where the base of the ladder to the base of the fence is X. The place where the ladder hits the building, this distance is H. If we come up with expressions for X and H in terms of theta and maybe even L, the length of the ladder, the cotangent of theta is X over 2. So X is 2 cotangent theta. That comes into play later. And H, you could say the tangent of theta equals H over X plus 5, but that gets really messy. If you say the sine of theta equals H over L, H equals L sine theta, then you can apply the Pythagorean theorem to this right triangle, which is what I've done here. H squared plus H plus 5, the quantity squared, equals L squared. But H squared is L squared sine squared theta, and X plus 5 is 2 cotangent theta plus 5, quantity squared, because I substituted this for X. And if I move this L squared sine squared theta over here and factor out the L squared, this is the cosine squared of theta. If I divide both sides by the cosine squared of theta, I get this. Then take the square root using the positive square root. You could leave it like that, but we're going to take the derivative, and it's easier to take the derivative if you divide cosine theta into both terms in the numerator, giving you this. So there's L of X, or L of theta. And I've rewritten that up here with the sine of theta in the numerator. You could also write that as 2 cosecant theta, but it's probably just easier to leave it this way. So the derivative is negative 2 sine theta, the minus 2, and then you have to take the derivative of the inside chain rule. Over here, same deal. There's the derivative of the inside. If you rewrite it in without any negative exponents, you get this. There's L prime, and we want to know when does that equal 0. So if we set it equal to 0, take this term to the other side, we get this. Cross multiply, you get this. How can we solve that for theta? Well, the trick is to divide both sides by cosine cubed theta, because sine cubed over cosine cubed is tangent cubed. These cancel out over here. So the tangent cube theta equals 2/5. So the tangent of theta is cube root of 2/5. And the inverse tangent of the cube root of 2/5 is 0.635 radians. And over here on Desmos, there's L of theta. There's L of 0.635. It looks like the height of the ladder, the minimum height, is 9.582 feet. Okay, to actually prove that that's a minimum, you could take the second derivative and apply the first derivative, the second derivative test, or you could apply the first derivative test to this guy. But it is a minimum, and I'll post a link to the Desmos graph that has a table of possible values for theta, and you'll see in that table that this appears to generate a minimum. There you go. Hope that helped. If you have any questions, post a comment.